Welcome back to the 16th video about the full fly-by-wire electric outboard project. In the previous video, we implemented the first version of our RS-485 bus protocol between the master and the slaves, in our case, the motor slave. Card here, link in the description. Anyway, in video number 14, we did some housekeeping in regards to the circuit and the code on our microcontroller. And at the end of that video, we also discovered a fatal design flaw. We are putting too much load on the voltage reference in our current sensor. Card here, link in the description. So in this video, we will redesign the circuitry on the analog side of our analog to digital converter to remedy that problem. Enjoy! Short recap of the problem. Our current sensor has a built-in voltage reference source, 2.5 volts plus minus 0.2%, so a really good one. And we feed that reference voltage directly into the reference input of our analog to digital converter. In addition, we use that VREF to feed our temperature measurement circuit. Card here, link in the description. That puts another 20 kilo ohm load to ground on our VREF. Moreover, that load is variable because it includes a PTC thermistor. On top of that, VREF is also supplying our water intrusion detection circuit. Card here, link in the description. It might be quite high impedance, but it's still putting some load on VREF. Here's how the whole thing looks in practice. I'm measuring here the reference voltage from our current sensor. It's currently 2.466 volts. It should be at least 2.495 volts. And now if I remove the PTC from the temperature measurement circuit, basically opening it up, we're at 2.502 volts. That's well inside the limits. It could be at most 2.505 volts. The question is now, are we now well inside what the voltage reference can supply, or are we just at the edge what it can take? Now, if we short out the sensor from the water intrusion detection, putting another, 590 kilo ohms to ground on that voltage reference, you see I can flip the last digit. Yeah. So we're really just now at the edge of what that voltage reference can supply. The reference input of our analog to digital converter has a current drain of typically 100 microamps. At a reference voltage of 2.5 volts, that's equivalent to a 25 kilo ohm resistor to ground. But the current drain can be as high as 150 microamps, and that would be a 17 kilo ohm resistor to ground. Since the datasheet of our current sensor has absolutely no information in it how much current you can draw out of that reference voltage output, we'll have to assume that it should be less than 100 microamps and that the load should be less than 25 kilo ohms to ground. Before we try to solve the problem of drawing too much current out of our voltage reference, let's have a look at the whole circuit and see if we can spot other weaknesses. For that purpose, I've drawn here the 5 branches of our circuit: voltage reference, current measurement, water intrusion detection, temperature measurement, and battery voltage measurement. I've omitted all filter and decoupling capacitors so not to clutter up the picture. We know our voltage reference branch is shite, but what about the current measurement branch? We have here a voltage divider to get the output from our current sensor from Vref plus minus 0.625 volts down to 0.8 Vref plus minus 0.5 volts, bringing it into the input range of our ADC between 0 and 2.5 volts. And that voltage divider has an output impedance of 1.3K. That's a little too high for our ADC, just a little, and we should slow it down to 1.9 megahertz. Also, we are using here only 40% of the ADC's input range, and that's for plus minus 0.5 volts. So for plus minus 50 amps. If we just look at a motor, not at a battery that can be charged, that reduces to 20% of the ADC's input range. We don't have to talk much about the water intrusion detection. The output impedance of that circuit is, beyond anything reasonable. That's why I designed in here a large buffer capacitor. Not a nice solution, as a longtime viewer remarked, but it's kinda working. The temperature measurement circuit with that 10K resistor and that 10K PTC is kind of okay. We got an output impedance of 5K. That means to avoid any errors, we should slow down our ADC to 1.7 megahertz. But then, slowing down the ADC to 1.9 megahertz, respectively 1.7 megahertz, should be possible without any problems. As we have seen, the battery voltage measurement works just fine. A link in the description. The voltage divider here, 11K and 1K, gives us an output impedance of 0.9K, and that's below the 1K our ADC wants if we run it at a full 2 megahertz. If you wonder where I got those clock frequencies for the ADC in relation to the impedance of the signal sources, there's a figure in the ADC datasheet that specifies just that. Now let's try to solve our reference voltage problem. And so we can keep track, I gave version numbers to each branch of our circuit from RV0 for the reference voltage to VV0 for the battery voltage measurement. So here's version 1 of the voltage reference circuit I came up with. Please note, our current sensor can accept an external voltage reference at its Vref pin as long as you supply enough current. So we built our own voltage reference that can supply enough current for everything. And we can use simply a shunt voltage reference, 2.5 volts, 0.2%. That will set us back about a buck. And a resistor up to VCC, 5 volts. And we're done. However, and that would be version 2 of our voltage reference circuit. For just about 50 cents, you get a really nice op-amp. I'm talking here picoamp input currents, rail to rail, and a DC offset in the range of maybe a few hundred microvolts. So we just take such a thing and buffer the voltage reference output of our current sensor. If we are already using an op-amp here, we could also use that op-amp as a non-inverting amplifier, boosting our 2.5 volt Vref up to 3.125 volts, the maximum output voltage of our sensor's Vout pin. That would be version 3 of our reference voltage circuit. Then we could feed the out of our sensor directly into our ADC, which has now an input voltage range between 0 and 3.125 volts. That would be version 1 of our current measurement circuit, which of course only works with version 3 of our voltage reference circuit. We keep a little resistor here, 1K or smaller, to make sure that the load on our sensors V out pin is at least 1 kilo ohm to ground. Typically our ADC has an input resistance here of 1 kilo ohm, but who knows? So better safe than sorry. Please note that this variant doesn't change the fact that we are only using 40% of the ADC input range for -50 to +50 amps, respectively only 20% for 0 to 50 amps. We now also have to change our battery voltage measurement circuit to work with version 3 of our reference voltage circuit, bringing the version number here up to 1. We're changing the voltage divider here so that at 30 volts input voltage we now get those 3.125 volts out into the input of our ADC. Please note that brings us quite close to the 4.7 volts of our protection Zener diode. Our margin is now only 1.575 volts. That is, we will have a little bit more leakage current here compared to version 0, where the margin was 2.2 volts. However, our resistor values are quite small, so that shouldn't matter. Okay, we're back to version 2 of our reference voltage circuit, just buffering our 2.5 volt reference voltage. The reason being, you can get 4 such op-amps in a package for the price of such a precision voltage reference. Now, let's see what we can do with 3 additional op-amps. So I present to you version 2 of our current measurement circuit. At its heart is a differential amplifier that moves the Vout voltage of Vref, so 2.5 volts plus minus 0.625 volts, to a range of 1.25 volts plus minus 1.25 volts. Using 100% of our ADC's input range, and of course impedance is no longer an issue with that version. Little caveat here, even if manufacturers call their op-amps rail-to-rail, I've never seen a rail-to-rail op-amp that can actually drive its output fully down to ground and fully up to VCC. There's always a little margin left. That means if we want to go 1.25 volts minus 1.25 volts, so minus 50 amps, we might see some clipping. But that doesn't really matter. If I use that circuit also for my battery monitors, I never will charge my batteries with a full 50 amps, more like 10 or 20 amps at most. We could do the same for our battery voltage measurement circuit. Our lithium iron phosphate batteries will shut off at 20 volts. So, for example, if we see 15 volts here at the input, something has already gone terribly wrong. Meaning we're currently only using about 50% of the ADC's input range. So in version 2 of our circuit, we are now also using a differential amplifier to bring those 15 volts to 30 volts down to 0 volts to 2.5 volts, using now 100% of the ADC's input range. Again, even when we're using a rail-to-rail op-amp here, we have to watch out for clipping when we come close to the ground rail. Now we could use our fourth op-amp to either improve our water intrusion detection circuit or our temperature measurement circuit. In case of the water intrusion circuit, that would be wasteful because we are really only interested here in the order of magnitude of the resistance of our sensor. And for the temperature detection circuit, I have other plans. When we developed the temperature measurement circuit, link in the description, I forgot to mention that there's a fourth kind of temperature sensor, and thank you to another long-term viewer for pointing that out. And that would be integrated sensors with an analog output, for example, like that LM253. That works like a shunt voltage reference, but changes its voltage with temperature. For example, at minus 40 degrees, it has a voltage of 2.6 volts. And at 100 degrees Celsius, it has a voltage of 4.0 volts. It's also only a little bit more expensive than our PTC thermistor. And more important, at the end you have a voltage output that is proportional to the temperature. Meaning you only need a single point calibration, which is always a plus when it comes to temperature stuff. With that resistor network, and please take the values with a grain of salt, I just did some back of the envelope calculations, we get an output range of 1.625 volts to 2.5 volts for that minus 40 degrees to 100 degrees Celsius range. That's only 35% of our ADC's input range. However, 1 degree C is equivalent to about 10 LSBs, so that's still okay. Also, the output impedance should be 0.94K, so we're golden there too. So, these were my thoughts about improving the analog side of things. Please let me know in the comments what you think about them and which variants you prefer. You can refer to the different versions of the circuits for that. Now here's the op-amp I was thinking about all the time. The Texas Instruments TLV9144. Supply voltage 2.7 to 18 volts. We will run that thing at 5 volts. Rail-to-rail input and output, we will have a closer look at that. Low offset voltage, plus minus 265 microvolts, but that's just typical. Yeah, another detailed look necessary. Low offset voltage drift plus minus 0.2 microvolts per degree C. Yeah, we can forget about that. Low flicker noise, 3.4 microvolts peak to peak. And high common mode rejection, 108 dBs. I don't believe that for a second. Let's have a closer look now, shall we? Input offset voltage, there we have the advertised 265 microvolts, but the worst case is 1 millivolt. That's a little bit high for my taste. I would have liked it below 1 millivolt, but then our voltage reference is plus minus 5 millivolts. Input offset voltage versus power supply. So, we shifting 0.112 microvolts per volt change in the power supply. Perfect. Channel separation, 106 decibels. That's more than 100,000. Actually, that's close to 200,000. So, perfect as well. Input bias current and input offset current. Worst case, plus minus 10 picoamps. Please note, 10 picoamps would cause a 10 microvolt drop in a 1 mega ohm resistor. So, we're scot-free there too. Input voltage range, The common mode voltage range is our negative rail, so in our case the ground, minus 0.2 volts, to the positive supply rail, so our 5 volt rail, plus 0.2 volts. So you can overdrive those inputs. How great is that? Common mode rejection ratio, when we run that thing at 5 volts, it's at least 86 decibels. That's again about-ish 20,000. Good enough for us. Input capacitance, differential and common mode. 500 gigaohms, 3 picofarads, 5 teraohms, 1 picofarad. Yeah, we don't have to worry about that. Gain bandwidth product at a very high load, admittedly, but it's 125 kilohertz. Meaning, if we would have the amplification at 100, we only had a bandwidth of 1.25 kilohertz left. But yeah, that shouldn't bother us. However, here, voltage swing from rail to rail, positive and negative rail headroom. And here is a little problem. There are only values given for 2.7 volts and 18 volts and loads between 2 kiloohms, 10 kiloohms and, well, no load. And if you took a closer look here at the numbers, you see that there is no linear relationship between the load and the supply voltage and the headroom we have to give that thing. Fortunately, we find further down a figure that gives us the output voltage swing versus output current for Vs plus minus 2.5 volts. So for a 5 volt supply. Perfect. And here we also find the first typo. The load axis here is not in milliamps. That's amps. Otherwise, the maximum load would be here 25 microamps. Anyway, if we do a little guesstimation here and draw in a line for 2.5 milliamps, that would be an output of 2.5 volts through a 1 kilo ohm resistor to ground, like for example our ADC inputs. We end up here, I don't know if you can read all these numbers, but we end up at 2.25 volts. That is, we need a headroom, or we need to stay away from our 5 volt rail at least 250 millivolts. Please note the supply voltage here was plus minus 2.5 volts. So the 2.5 volts here is really our VCC rail. If we put another 1 kilo ohm resistor in series with our ADC inputs, which is perfectly fine, remember a source impedance should be 1K or lower, we get a current at 2.5 volts to ground of 1.25 milliamps. And then doing the guesstimating here, we end up at 2.40 volts output voltage, again symmetric, plus minus 2.5 volts supply, so a headroom of 100 millivolts. We have to stay below our 5 volt rail. And that's what I meant when I mentioned before that I've never seen a rail-to-rail op-amp with a real rail-to-rail output. So, what do you think about the TLV9144 quad amp for our application? If you know of another quad op amp at that price point, so about-ish $1 when you buy 10 of them, that is even better. Please let me know in the comments. I have one more idea to improve things. That's not so much related to resolution and precision, but to noise. Currently, we're supplying our analog circuitry from the 5 volt Arduino rail, which is created by a switch mode power supply and sees all kind of digital noise. How about we supply our analog circuitry with a linear regulator that is fed from our 9-volt switch mode power supply? We are consuming approximately 31 milliamps, maybe a little bit more, so a little 100 milliamp linear regulator should do the job. And there I stumbled about the ST-LEO5AB, a linear regulator with a precision of 1%. Moreover, it specifies the supply voltage rejection up to a frequency of 10 kilohertz. To be exact, 60 decibels at 10 kilohertz. That's one of the few linear regulators that do that. Most just specify the supply voltage rejection at 120 hertz, and there this thing got a whopping 82 decibels. And if I interpret that little graph they provide in the datasheet right, at 100 kilohertz, we still should have 40 dB supply voltage rejection. So that thing should really be able to filter out all the noise coming from the switch mode power supply and provide us with a really quite 5-volt rail for our analog stuff. Though it's not quite cheap. It comes about 75 cents if you buy 10 of them. What do you think? Let me know in the comments. That's it for today. I know, a rather theoretical video, but I think that was necessary to make really progress on the analog side of things. Anyway, I don't know when I'll be able to order the parts or when they arrive. So I can't really say when we continue, but there will be a video next week. So till then, bye.